Hello everyone. In this quick tutorial slash overview, we will discuss how to use the updated down API to import external textures into WebGPU, and more precisely, how to use this API to import a video stream generated with FFmpeg in a DirectX 11 context. To implement this feature, I built a dedicated VideoPlayer component in my NervLand engine, and here is an example of the usage of this component, displaying a recording of a gameplay session from Ghost of Tsushima inside the TerraView test application. So I guess you might be familiar with this view, which is the same as what we have in the TerraView 8 demo application. So here there is nothing too fancy really. We just start playing the video file on the start of the application, and that's it. We have no way to pause the playback or to rewind or to resize the window or anything. But well, we really have to start somewhere anyway, right? Now, before we go further into the implementation details, please note that I have also prepared a dedicated folder in the NervLand Adventure repository to share the files relevant for this video import feature. So if you are interested in this, you could have a look at the repository available at this location, and I will make sure to provide a copy of this URL in the video description. And from there you just need to go into the experiments, and if you go into the folder for the FFmpeg video playback, you will find the most important files that are necessary to implement this feature on my side, but you can also use that as a reference on your side. Now, please note that those files will not compile out of the box. They are just provided as reference, and you need the NervLand sources to build a complete framework. So that's just to give you some indication on how to proceed. Now, how does it work? Let's start with a simplified overview of the design. We start here with a regular video file, which in my case is some gameplay recording, as I mentioned, in MPEG 4 format with X264 encoding. And then we'll be using the FFmpeg library, configuring the decoder in the library to use the hardware acceleration and to produce a video image stream directly on the GPU in a DirectX context. Then we will copy the resulting DirectX texture into our WebGPU context using the new shared texture handling API from down. And finally, we can process the final WebGPU texture as any other regular texture and display it in our application, which is, for example, what I'm doing here on a simple quad. Now, this is all just a very simple and minimal implementation with a lot of limitation for the moment. So in the NervLand code, I have added a VideoPlayer class, and this class itself contains an abstract video decoder class. And next, I have added a concrete implementation called FFmpeg video decoder, and this one depends directly on the FFmpeg binaries. And so as such, I am currently only building this module in the native version of my application, so on Windows, and well, technically also you could do it on Linux, but not quite. And yeah, the point is there is currently no real support for the WASM version. You could in theory build the FFmpeg binaries with unscripted and get that working in the browser directly. But I'm not really interested to go into this direction for the moment, because I guess it's going to be a bit complicated, and there are, I guess, also licenses consideration that will come into play. So let's just not do this for now. And then on top of that, the implementation I have is only working for Windows for the moment. And I'm kind of explicitly requesting to use DirectX 12 backend, but I'm not quite sure we really need that in the end. Maybe it could also work if we use Vulkan backend, but I didn't try it. But yes, for the FFmpeg side, I am only really using the DirectX 11 video acceleration pipeline. So yes, there is still quite a lot to test and to investigate on this topic. But anyway, let's get started with some analysis of the code used to render this video clip. So first, in my Terrain View app, I'm now starting to progressively implement and use a configuration system to create some additional scene content on the planet. So even if this is not directly related to the video playback layer, for reference, here is the YAML element that I'm using on my side to request the creation of a simple quad at a specific location, and on which we will render the video stream from this video file. Next, we will use this video surface blueprint to construct an actual video surface object in this method, construct blueprint. And in there, what is important to us is this create video or fallback area. If there is indeed a valid video file, this will eventually call create video area. And as you can see here, we start with creating a video player. Then we need to keep track of this video player actually, so I really need to keep a reference on it. And then we specify the texture and the location on the texture where I want to copy the video frames. And after that, we call the play function on the player. When we create the video player, the first thing we will do is to create this FFmpeg video decoder. And after that, if the video file is provided, we're going to open the video file. The constructor for the FFmpeg video decoder is really not doing much. It's just going to call this initialization function for the network support, but I'm actually not even sure we really need that. The actual work is going to happen rather in the open file function for the video player, because this is where we will call this open input on the decoder. And after this step, we may eventually call play if we were requested to do it. In the FFmpeg video decoder open input function, we will eventually call this initialize decoder, which is the main thing that we do here. And this method here is pretty large, as you can see. Yet, what is really important, I think, here to mention is only this part, where we will request and set up the hardware decoder for the codec. So again, sorry, but this method here is also a bit messy, because I was really trying to test with DirectX 11 and DirectX 12 support on the FFmpeg side, but yeah, in the end, the support for DirectX 12 is not really working properly yet when it comes to copying the DirectX texture into the WebGPU context, so we're not going to mention that for the moment. Anyway, what we do here is that we start with allocating a buffer for the hardware device, giving it the type that we want to use for this session, and in our case we specify here that we use the DirectX 11 video acceleration. Next, we can specify the device that should be used on the FFmpeg side to perform any DirectX operation. Technically, we don't really need to do that, because if you have access to the output texture in the hand, you could still retrieve the device from the texture and use this to perform additional operation with the DirectX 11 device. But since I have this convenient library where it's very easy for me then to manipulate the device, I thought I could just as well use it here. And finally, we're going to call this init function on the hardware device, and this is where you will know that everything is working as expected for the hardware acceleration or not. So if there is no error for the hardware device initialization, you are simply then going to allocate the context for the codec and specify that you should use the hardware device for this context. So then this codec context will be ready to start decoding the video frame with hardware acceleration. So with the FFmpeg decoder ready, the process continues then with the call of the play function of the video player. And in this function, the main idea is really just to set up a callback that will be executed on every frame. So in the WebGPU engine. So on every frame, we should call this update method. So in this update method, we're simply going to use the current time that we have for the complete application, complete execution time, and also the video frame rate. So to be able then to compute what should be the expected frame and figure out if we should request a new frame to the FFmpeg decoder. And if it's the case, then we're going to call this decoder decode next frame, which may fail actually if there's no frame anymore. So in this case, we stop the playback, and otherwise we need then to copy the data from the decoded frame into the target texture that we specified for this video player at the given location. So here the decode next frame itself is not very interesting because this is just going to process a stream of packets until a new frame is completed. So let's just move directly to the get current frame implementation, as this one requires some additional work. So for reference, here is the first part of the code in this method, and in fact this is where things start to get a bit tricky as we have a few issues to handle. First, when performing the frame decoding, FFmpeg will produce texture with the format which is the XGI format NV12. And yeah, this doesn't have much to do with RGBA, unfortunately, so you can't really use that to render your frame and display some graphics. Next, the generated output that we retrieve here, this texture, D3D texture, it's actually constructed with the bind decoder flag. So again, that's a problem because this flag is not compatible with the bind shader resource, which you would normally use to be able to do something with this texture when you use it as an input for some kind of shader. And the thing is that, yeah, this flag here is specified to indicate that the texture is really optimized for the video decoding processing on the GPU. Another issue that we have is that this texture, of course, doesn't have any shared flag, so we won't be able to directly share this with another DirectX context or another GPU context anyway. And finally, this is actually a texture to the array, which means that on every frame you also need to retrieve an index which is going to tell you what is the layer in this array which contains the complete frame that you want to retrieve. To resolve the bind decoder issue, we need to copy the layer of interest from the input texture into an intermediate texture, which is still using the NV12 format, before we can do any additional processing. So we create this texture once. This is this NV12 texture that we create here using this using the DirectX 11 engine that we have, and we make sure that this texture will have the bind shader resource flag. And next, on each copy cycle, we will get from the source texture the layer of interest, and we will request to simply copy from this source texture into this NV12 texture. And the nice thing with this is that we're also dealing with the point number 4 that we mentioned, the fact that initially we have a texture to the array, but if we only copy one layer from this texture to the array, we will end up with a simple texture 2D. Next, we will need to convert from the NV12 format to RGBA. So we'll do that also in the DirectX 11 side. And we'll need another destination texture to store our conversion result, which we will call RGBA texture, which is here. And while we are at it, we can also build this as a shared texture to be able to import it later in the WebGPU context. So we'll use this create read-only shared texture, and that's going to give us the shared envelope that we need to access this texture from another device or another context. Next, we have to execute the compute shader that will convert the NV12 texture into RGBA. So we specify the shader here, we specify the destination as an unrendered access view with this RGBA texture, and we also provide here two shader resource view, the luminance shader resource view and the chroma resource view, which are both from the NV12 texture. Actually, here is the code that we use to create the luminance view from the NV12, and yeah, we'll see that here we're going to use this R8 unorm format, and then here is the code that we use to create the second one, the chroma shader resource view, again from the NV12 texture. But now you can see that we are instead going to use this R8 G8 unorm format. So it may be a bit surprising at first that you have a single texture and you get two different views like this on it, but that's actually some kind of internal behavior from the DirectX 11 API. You can really specify this on this NV12 format, and it's going to provide you the luminance plane on one case and the chroma plane on the other case. Actually, if you want more information on this, you could go to this URL, which I'm also going to put in the video description, and this is going to provide you the description of all the formats that you have available in the XGI. And on this page, if we look for NV12, you will find this section, and in there, this part here is a description of what I just mentioned on how to get the shader resource views for those two planes. Now let's have a look at the NV12 to RGBA conversion shader itself. First, the shader declares the input and output resources that we'll use. So we'll see that we have the luminance texture and the chroma texture that are provided as input. And also we have this writable texture, which is the output where we write the pixel value in RGBA format. Next, we have the core of the logic used to perform the conversion. And what you need to know is that when we use this NV12 format, we are actually really dealing with this YUV vec3 per pixel, and once you have those YUV coordinate, you can very easily convert them to RGB with this function. The only thing is that with the NV format, you get the Y value for every pixel, but you get the UV values less often because they are shared between groups of 4 pixels. So here is actually the main function of the compute shader, and you see that after doing some check of the bounds, we can retrieve the Y coordinate using the coordinate that we want for the pixel, and then we can retrieve the UV coordinate, but here we have to be careful and divide those coordinates by 2 because we only have half of the resolution for this plane. But still, after that, we can construct the vec3 or the float3 with the Y, U, and V coordinates, and you can convert that directly to RGB. And that's pretty much all you need, because then you can simply write those RGB coordinates into your output texture. The thing is, normally you would probably use this first line here, writing into the coordinate of your current pixel, but in my case I have a special convention in NervLand and I need to flip the image vertically, so I'm doing that immediately and inverting the Y coordinate here. After the compute shader is executed, we have the content we want in RGBA 8 format in our DirectX 11 shared texture. So the second part of the frame update logic is to perform the copy of this RGBA data from DirectX to some location in the WebGPU context. And to do that, we use this code. So this is probably starting to feel a bit unusual, even if you are used to a DOM library. And to be honest, I'm not completely sure myself. This is how it is intended to be used, and yeah, maybe there's a better way to do it. But still, it's pretty hard to find any detailed information on the internet on this topic for the moment. So yeah, at least this is working for me, so I will stick with this for now. So as I just say, the key point here is that we want to copy the DirectX 11 RGBA texture to another container texture in WebGPU, which is in fact the location that we provided initially, if you remember that part. To access the DirectX 11 texture, we're going to use this texture interface, but whenever we want to access that object on the WebGPU side, we need to encapsulate that access with a pair of begin access call and then a end access call on the shared texture memory object that we use to create the texture interface. I'm really not quite sure why we need to do that, but if we don't do it, it doesn't work. At least it was not working for me. And yeah, in between those two, we're going to use this copy pass, which is a compute pass in WebGPU, containing a simple compute node with a compute shader. That's, well, it's just a simple copy actually, so I'm not going to give some additional detail on that because it's just a matter of taking an input texture in RGBA 8 and copying that into a simple other destination texture, so nothing really fancy here. But what I really think we need to cover instead is how we create the interface texture itself, and this is done with this code. So first we have this structure here, which is going to be used as a container for the shared handle that we have from the DirectX texture, and we chain that into another descriptor, and that's what we're going to use and to create the shared texture memory object. And in fact, the function here that I have on my engine is really just going to call directly the WebGPU device function import shared texture memory. So you will find this function directly in the WebGPU header file. Once you have this shared texture memory object, you don't need the shared handle anymore, so you can close it. And the second part of the logic is then to create a texture interface, and for that you just need to provide a texture descriptor with the usage that you want and the size which it actually match the size of the data that you have into this memory block, and you specify that the format that should be used for the texture. And after that, you call this create texture on the shared texture memory object, and this will in fact be also part of the WebGPU header, and that's going to provide you a, well, completely regular texture object. And well, this is it guys. With all those elements put together, we can then extract a stream of video frames from the source video file and get them fully imported into WebGPU with complete hardware acceleration. Yippee! So yeah, now just to recap, here is an overview of the workflow that we use to copy all those frames. We started with a texture to the array provided by FFmpeg in NV12 format, and with this decoder, this bind decoder flag. So as we said, we could not really use this for anything, so we have to do a simple copy first, and in the process we're going to extract the layer of interest, which is also provided directly by FFmpeg. And in the end, we get here a new texture where we can provide the bind shader resource flag. Then we have to do the conversion from the NV12 format into the RGBA format. For that, we're going to use a dedicated compute shader, provide the luminance and chroma plane from the texture as input, and write directly into the output texture. But the output texture here, when we created that, we made sure that it would be also a shared resource that we could use in another context. So we have a shared handle for this texture. So the next step then is to use this shared handle to create the interface texture, which correspond to the memory block where we have the data for this DirectX 11 texture. Once we have the interface texture, we can just do whatever we want really from this point, but in my case I need to copy that into a bigger texture, which I'm using as a texture atlas for multiple processing. And so we do a simple copy of the data here, and that's where you actually get the data really into the WebGPU memory part. Now, one thing I should mention is that we could also, in fact, do it differently. You could consider doing the conversion from NV12 to RGBA when you are already in the WebGPU context. So for that, you would need to also make this texture here shared and create a shared handle that will give you an interface for this format, and when you are in a WebGPU, you would then convert that to RGBA. I mean, if you need RGBA, maybe you need just NV12. And there are actually additional functions in down now that you can use to get the different planes from the NV12 textures, so you can get the luminance plane and the chroma plane as we did. But yeah, I didn't really want to go this way because this was adding an additional layer of new stuff, so yeah, that would be a bit too much at the same time. So this path, I guess, is slightly easier and more conventional. And here we are for this FFmpeg WebGPU integration tutorial. I hope you learned something here. And in case you want to look into this more carefully, as I mentioned at the beginning of the video, feel free to check the resources shared on this topic on the NervLand Adventure GitHub repository. And of course, if you have any question on this, feel free to leave a comment. Also, please like the video if you found this content interesting or useful to you. And see you next time. Bye bye.